It's a journey to the center of our solar system. A mission to gather information about the most critical celestial body in the sky, our star, the Sun. September 1st, 2019, marked the third perihelion from NASA's Parker Solar Probe. That's the closest point to the Sun during one orbit, the distance of about 15 million miles, this time tying its own record, closer than any spacecraft has ever been.
We're going to go closer to the Sun than any other spacecraft's gone before. We're not going to do that once. We're not going to do it twice. We're going to do that 24 times. And that is terrifying.
To be sure, the Parker Solar Probe already has and will continue to explore uncharted territory, getting closer and closer during its planned 24 passes, ultimately entering the Sun's outer atmosphere, known as the corona, a maneuver some are calling touching or kissing the Sun. To achieve that, the spacecraft will fly by Venus 7 times using the planet's gravity to slow down, alter its trajectory, and tighten its solar orbit. If all goes according to plan, nearly 7 years after its mission began, the probe will eventually swoop within 3.8 million miles of the Sun's surface. That's 96% closer than our location here on Earth.
We are counting on success and longevity of the spacecraft to be able to accomplish that. But you know, it's our own star, and it's the first mission to the star.
The mission amazes even the man it's named after, Eugene Parker, the physicist who first theorized about the solar wind, the steady stream of charged particles emanating outward from the Sun throughout the planetary system and beyond.
This is a journey into never, never land, you might say, where it's too hot for any sensible spacecraft to function, but some very clever engineering and construction has succeeded in making what looks like a very workable instrument.
A $1.5 billion, 1,400-pound tool designed to collect data to help us better comprehend the mechanics of the Sun.
We don't understand the Sun, and when we look at it, we're trying to figure out how does it work? And a lot of that is how does it work so we know how it affects us.
Like explosive coronal mass ejections and the causes of space weather, which can disrupt Earth's satellite systems and telecommunications, the nervous system of today's modern life.
If you have large amounts of this charged material coming into the Earth's atmosphere, it can actually disrupt power grids. It can blow them out. So basically, it can introduce surges of power into our power grids and take down large power grids across the world.
It's happened before. Most recently, March 13th of 1989, in Quebec, Canada, leaving 3 million people without power for more than 7 hours. An event which shut down nearly all transportation systems and cost $10 million in lost revenue.
We need to understand very close up how the Sun sheds these huge clouds of material called coronal mass ejections, and how these went their way through space to the vicinity of Earth, and which ones are going to hit Earth and which ones are going to miss Earth.
Information gathered by the Parker Solar Probe could help lead to better forecasting of such destructive space weather and enable better preparations. The Parker probe also seeks to understand the magnetic properties of the Sun, helping to answer another basic question that continues to puzzle scientists.
Why is the solar corona, the outer atmosphere of the Sun, at 1 million or 2 degrees when the Sun itself is only 5,600? It isn't because of sunshine, that's for sure.
the only way that you can really get the ground truth is to go there, so to speak. And that's what the solar probe is going to do.
5, 4.
Parker Solar Probe's mission began under the cover of darkness, atop a Delta IV Heavy rocket, launched the night of August 12, 2018. Out of view of its ultimate target, the Sun, but not its namesake.
There we go.
Wow.
It was the culmination of 6 decades of scientific dreams and hard work, dating back to when Parker first published his solar theories in 1958.
Parker's solar probe really is a historic mission. It was first dreamed of in 1958, and it's remained the highest priority mission throughout that period. The reason it hasn't flown is just because it's taken a while for technology to catch up with the dreams that we had for this amazing mission.
In particular, advances in materials engineering, which led to the development of the critically important 7.5-foot wide, 4.5-inch thick carbon composite heat shield. It's got a white reflective surface and weighs 160 pounds.
You're going into an environment that's completely unforgiving. The temperatures that we're seeing on the spacecraft have not been seen by any other spacecraft ever before.
The Parker Solar Probe is a technological marvel. The thermal protection system, the heat shield, will be glowing cherry red.
When we're at closest approach, the front surface of the heat shield will be at about 2,500 degrees Fahrenheit. The back surface of the heat shield will be about 600 degrees Fahrenheit. But then the spacecraft bus is basically sitting at 85 degrees Fahrenheit. So the shield is actually really keeping everything very cool.
Including the full complement of equipment and sensors aboard the spacecraft, allowing the 4 primary instruments to complete their scientific tasks, taking measurements of the Sun's electric and magnetic fields, collecting data about the origins of the Sun's high-energy particles, the solar wind density and acceleration, as well as taking images of the solar environment by looking around the heat shield.
We sort of peek over the edge of it. We use it as a shield to block out the sun itself, and that allows us to see this very faint glow coming from the corona that's only observed during an eclipse, for example. We're creating an artificial eclipse. Well, eclipses are great, but from the data point of view, I like my instruments better.
The initial download of data from the first 2 perihelions was completed May 9th, 2019. 22 gigabytes. 50% more information than the team anticipated, including this image of the solar wind moving left to right. That's the Milky Way moving off screen, and the bright spot coming into view is Mercury. Due to all its immediate success, for the 3rd solar pass, the research team decided to activate the probe's suite of scientific equipment over a stretch nearly twice the distance they operated during the first 2 opportunities, an increase of 14 observation days. Of course, even before its first encounter with the Sun, the pioneering probe began breaking records, surpassing 153,454 miles per hour, quickly making it the fastest human-made object relative to the Sun. Its speed at the 3rd perihelion was similar to what it was during the first 2, 213,200 miles per hour. Yet another record. But still, only half of the 432,000 miles per hour expected at the 24th and the last close-range solar pass. But before that time comes, the Parker Solar Probe will undoubtedly make major contributions to our knowledge of the Sun, perhaps solving the questions it was sent to investigate, or maybe posing new ones. Either way, the man who inspired the mission thinks it will all be worth it.
I have always said, on a mission like this into new territory, you're going to be in for some surprises. Maybe not big ones, maybe only little ones, but you're going to find that your point of view will have to change to conform with the data. And that's the fun part.